Swayam Prabha. Digital India. Educated India.
So, in this lecture, I will start a new module that is well foundation, and before I go to that well foundation part, quickly I will give one information that related to that uplift capacity of the pile, or I can give you the anchor pile or anchor plate, because uplift capacity of the pile I have discussed in the last class, and then that way you can determine, but there is another approach also where you can determine the uplift capacity of the pile, or you can say it is the anchor pile, or uplift capacity of anchor plate, or uplift capacity of foundation also. Okay. So, that is given by Maroff and Adams, it is 1968, which is in for clay, which is the same as the uplift capacity of the pile. There will be a addition factor into the undrained coefficient into the area divided by weight of the pile. So, that means the friction resistance plus the weight of the pile. So, addition factor you can take same as the addition factor under compression, and then this way you can determine the uplift capacity of the pile in clay, or I should not say it is the pile, it can be anchor plate, it can be foundation also, uplift capacity of the foundation, and then it is for uniform diameter. So, suppose if it is for enlarged base, then that means base or the that I was talking about, if it is a kind of this kind of foundation, or it is in kind of anchor plate. Okay. So, or you can say this is the enlarged base of the pile, and then how we can get the our uplift capacity of the pile. So, in previous case, in previous lecture, this is the only pile, but it can be treated as anchor plate, it can be treated as foundation, it can be treated as pile also. So, that is why I have kept it in a separate lecture. So, discuss this one. So, for the pile in enlarged base, this is for the enlarged base whose base is say dB. Okay. So, in that we can determine by using this lower of these two value. That means, here this is the L is the length of the pile or the foundation. Okay. And then we can get these lower of these two value, and we will get the uplift capacity, where K is generally taken as 1.1 to 1.25 for soft clay, 0.7 for medium clay, and 0.5 for stiff clay, because there is a K term is there, and that is a Nu, which is same as Nc under pile under compressive load. Okay. So, that also you can take, this is the uplift coefficient, can be taken as Nc for downward load. So, that is same as the Nc that we can take. Now, similarly for C5 soil, that for shallow depth, if the foundation is in two cases I consider, that pile will enlarge base. So, I am taking two cases, this is the central line. So, this is the shallow depth. So, that means, if your L or length of the pile. So, this L is the length of the pile. If L is less than the dB, okay, then I will use this equation. Then I will use this equation for C5 soil. Okay. Then there is a term S, and then there is a term Ku. Okay. So, these two we have to determine. Now, if for the great depth means, suppose the failure line will go up to a particular length, beyond that failure line will not extend, but your length of the pile is more than that. Okay. This is the h up to which failure line is been extended, and this is length is more than the h. So, h is the height up to which failure plane is been extended under uplift, because this is under uplift. So, previously also this is also under uplift. Okay. So, then this is assume that there will be a block which is moving up, here also this is assumed, that is why is adhesion factor L is alpha is taken as 1, because then in such case the adhesion is between soil to soil. So, and then this is the value, then how I will calculate the, so what are the unknowns we have to calculate? We do not know what is the h value, we do not know what is the Ku value, and we do not know what is the S value. Other parameters are known, Cu is known, dB is known, unit weight is also known, L is known, L is the length of the pile, but you have to know what is this value Ku and H. So, for the grade depth, either you can use this equation or there is a upper limit also, this is the upper limit. Okay. So, that means this value should not be greater than this equation, which where sigma v is the effective vertical stress at pile base. That means, at this point we have to calculate sigma v bar, and NQ is the your same as the NQ that we use for the foundation. Okay. Or you can use it for the pile under compressive. So, NQ, the same NQ we can use for pile under compressive. So, now I will give you how I can calculate the Ku, H and S. Here also NC and NQ same as the pile under compressive load, we can use those NQ and NC as suggested by Mayerhoff, and that we can use here. Okay. So, and then we have to determine the H and Ku. So, Ku is the earth pressure coefficient, which is 0.9 to 0.95 of phi value, and it is in between 25 to 40. So, Ku part is over. M is the coefficient depends on the phi value, and H is the limiting height of the failure surface. S is the safe factor, which can be determined by using these expression, and the maximum value of the safe factor is this value. So, now let's explain that how we can use these things. So, suppose this is for the phi. So, this is H for different phi, this is the H by BD. So, we know the BD width of the foundation or pile base, then using this table different phi value we will get the H. So, from here we will get the H value, H value is we will get that. So, we will get the H value from this here, because we know the dB, we will get the H value, and we will get the M value also here, and we will get the S max also here. So, once we get the M value and the H, then I will calculate the S from here also. I know the L, I know the dB, and I will get the M from this table. So, I will get the S value. So, S is known. Once I get the H, I will check whether that L is greater than H or not. Okay. So, if it is not, then I have to use the previous equation. Okay. And if it is L is greater than H, then I have to use this equation. And so, that means H part is gone, I know the H, Ku value is given, Ku I will get, and S also I will get, because I will aim from here, and then I will determine the S by using these equation. Now, in this equation I know M, I know L, I know dB, but then I have to check the S that I am getting is within S max or not. If it is within S max, then I will get that H, that S, and if it is greater than S max, then I will use the S max value. Okay? And then other equations are straightforward that we can use. Remember that the NC, NQ, this coefficient I can use, or this factor I can use the same as under piles under compressive load. Alpha value also I can use for uniform case, the same alpha pile under compressive load, and these other factors are I have already explained. The two cases, one is if the failure surface within the pile length, and if the failure surface is up to the pile length, or I should say one is the pile length is above the failure surface and another length is pile length within the failure surface. So, that I have to check by calculating h and the length, and then I have to check which condition I have to use. So, these are the equation for enlarged bed. So, if it is shallow depth, then I will use the equation A. If it is great depth, then I will equation B. But remember that these value, either you use equation A or equation B, should not be greater than the upper limit. So, upper limit will be this one, and that is the upper limit. So, diameter dB is the diameter of the base and d is the diameter of the shaft. Okay. So, that means what is the difference between dB and the d? Suppose this is the diameter of the base, dB, and this is the diameter of the shaft. So, this is the difference between diameter of the d and dB. Okay. Other things, and Fs is the frictional resistance. So, that means for it is, if it is a C5 soil, then you can calculate the Fs value, and A's value is the area of that shaft, then that will be your Fs. Fs is the ultimate shear resistance, and As is the area of the outside area of the shaft. So, this you have to check, and then you will get the uplift capacity of the pile. So, this is another approach, but I have discussed another approach in the previous class also. So, you can use both of them. So, but generally I will prefer to use the uplift capacity of the pile by using the approach that I have discussed in the previous class. But this is a general one, you can use it for the pile, you can use it for the anchor plate, and this is the uplift capacity equation for a general kind of solution. So, next one I will discuss the well foundation. So, this well foundation is sometimes called as the cushion foundation also. So, the advantage of this cushion or the well foundation, this well foundation provide a solid and massive foundation for heavy loads and useful where loads have to transfer to a deep soil strata. The construction is easier than the driven pile in case of dense sand and the polder, okay, and can be used effectively where the uplift loads are high and have higher resistance against the lateral load. So, that means here I can replace this well foundation or I can replace the say group of piles or number of piles by providing well foundation, that is also one advantage. So, now this well foundation can be different types. Okay. So, first one is the open well or the open cushion. So, here you can see this is the plan and the cross section. So, this is a circular cushion and this is a rectangular cushion, and here this is a section. So, this is the soil or the where the foundation we have to install, and definitely above that it is the water table or water. Generally this type of foundation are suitable for the bridge structure, for the bridge. So, that means, and it will be most of the time constructed within the river bed. So, that is why there will be water, then the river bed, and then I will discuss how we will determine the depth of this well. We have to determine the scour depth, and based on that we have to determine what would be the foundation depth or depth of the well. So, now we are discussing what are the different types of well and how they are constructed. Okay, so, this type of open well, they are top and bottom portion. So, this is the top portion and this is the bottom portion. So, they are open during the construction. So, they are concrete shaft. So, this is a basically hollow cylinder kind of or hollow shaft kind of thing, where there is this is the concrete which has the thickness, and then it is the hollow and open, it is also in the top it is open, bottom is also open. So, this is a hollow shaft which is remain open at the top and at the bottom during construction. So, that means this hollow shaft is been constructed within that soil and during the within the river bed or the soil, and during the construction this bottom and the top will be open. Now, this well is sunk and the soil from the inside the shaft is removed until the bearing strata is reached or required depth is reached. So, that means first it is sunk with into the water, and then when the soil which will be within the shaft, because the lower part is open. So, that means soil will come within the shaft. So, that soil we have to continuously remove during the construction process or during the installation process. So, until it reached the required depth or a bearing strata. So, that means this soil inside the shaft is removed. Once it is reached inside the required depth or the bearing strata, then concrete is poured into that shaft, because now this is a hollow shaft where which is installed up to the required depth, but water is still inside the shaft. Water is not removed, only the soil which is removed inside the shaft, within the shaft. So, there will be water, but once it is reached the required depth, then the concrete is poured within the shaft and the underwater. That means, it is water is there within the shaft and the concrete is poured, and to seal the bottommost part of the bottom part of the well. So, that means, top part is open, bottom part is open. Now, once it is reached at the bearing strata, this concrete is poured through underwater to form a seal at the bottom of the shaft. So, now the bottom is sealed by concreting, and then once the concrete seal hardens, then the water is pumped out from the inside the shaft. Now, once the concrete is hardened, then water can be pumped out, because before if you pumped out the water, then water surrounding that portion will again enter into the shaft. So, that is why the bottom portion of the shaft is sealed. Now, the water is pumped out once the seal or the concrete seal hardens. Now, water is pumped out from the soil from the shaft, and then now within the shaft there is no water, even there is no soil also. Concrete is at the bottom of the shaft. Now, inside that portion is filled with now sand generally or concrete. Now, this inside portion is filled with sand. Now, this type of well can be constructed up to a depth, up to a great depth, any depth, and it is cost is relatively low. The progress of construction in boulder deposit is very slow. So, the advantage is can be installed for any depth, but it cost is very low. But the disadvantages are the progress of construction in boulder deposit is very slow, the lack of quality control over the concreting, because concrete is now concreting is done underwater. So, quality control is very difficult for this type of construction. So, the quality control over the concrete poured into the shaft for the seal is very difficult. The bottom of the well cannot be inspected or cleaned out. Okay. So, because bottom is on the surface, so it is cannot be inspected properly and cleaned out. So, one day it is sealed by the sand, filled by the sand, then the top plug or the top portion is concrete is done, and then it is sealed. So, this is the total construction process for the open caisson. So, it has some advantages and the limitations also. So, the next one is the box caisson, where the bottom portion is closed, but top portion is still open, and they are constructed in the land and then transported to the construction site. The previous one was constructed in the site itself, but here it is constructed in the land and then transported to the construction site, and they are generally sunk into the site by filling inside the sand, ballast or concrete, because now the bottom is sealed. So, water cannot enter. So, but they are sunk into the water by placing sand or ballast or concrete inside that shaft, and they place up to the required depth, where there should be a previously leveled foundation base, because if the foundation base is level, then this type of caisson can be useful or can be installed. Okay. So, they are placed previously leveled foundation base. So, they are used where loads are not heavy and bearing stratum is available at a shallow depth. The advantage is the cost is this type of construction is low, and the disadvantages are the bearing surface or foundation base must be level or should be leveled before it is installed. Then care has to be taken to protect the foundation bed from the scouring action. The next one is the pneumatic caisson or the well. So, these type of caisson are generally used for up to a depth of 15 to 40 meter. So, this type of well is used when the excavation cannot be kept open, because what is the difference between this one and the first one? In the first one, both bottom and top are open. So, sometimes if it is not possible that the excavation cannot be open, because soil can enter or water can enter. So, in such case this type of caisson can be done, or can be caisson or well can be used. So, here what is that there will be a construction or working chamber. So, this is working chamber. So, where worker can work within that working chamber. So, height of the chamber is at least 3 meter. Okay. So, this chamber worker excavate the soil, because now here, because if it is difficult to keep the excavation part open, because in the first open caisson the excavation is done, but that the bottom is still open, but sometimes it is very difficult to do that, or if it is not possible, then you will go for this type of caisson. So, where working chamber, under this working chamber this worker excavate the soil, and then here air pressure in the chamber is kept high enough to prevent water and soil entering. So, as I mentioned that there is a possibility of entering the soil and water within the excavation. So, that means here the high air pressure is maintained within the working chamber, so that water and the soil cannot enter within the working chamber. So, that is why we have to take care the health issue of the workers, and if required, then there will be a rotation of the workers within the working chamber. They cannot be work for long time within that chamber. So, there will be a shorter duration of the working period for the worker, because if we provide the very high pressure within the working chamber. So, now there is a shaft, and within the shaft there is a ladder. So, this worker can leave and enter the chamber through this shaft in the means of ladder. This shaft can be also used to remove the soil and placement of the concrete. So, multiple shafts are used for large caisson construction, and airlock is provided to each shaft, obviously, because worker has to be inside the worker will work inside the chamber. So, that means here when the soils are excavated, those soils are removed through the shaft, and later on these will be used for the concreting purpose also. So, now this type of caisson is seen gradually as excavation proceeds, and when the bearing strata is reached, the working chamber is filled with concrete. So, that is act as a bottom plug. So, that means working chamber is sealed. Now, for this type of caisson, better control in sinking and the supervision is possible. Now, bottom chamber can be sealed effectively, because now there is no water when the concrete is being done for the seal of the bottom part, because it is done under dry condition. So, better quality control during the concreting is possible, and obstruction during the sinking such as boulders, which is a problem in the open caisson, that can be also removed, because water that worker can within the working chamber can excavate the soil. So, that issues can be solved. So, but the disadvantages are that this is a very costly method, and this type of well can be used up to 30 to 40 meter. Okay. And for the open caisson, it can use for greater depth, for even for more than 40 meter also. So, these are different components of well. So, this is as I was talking about this is the bottom plug. Okay. So, this is the concreting, this bottom concreting, this is the sand filling, then again the top plug and then the well cap. So, these are this is the plan and this is the section, this is the well and then is the piers, bearing and then the girdle. So, this is a bridge construction. So, what are the different components? That the well cap, this is the well cap. Okay. This well cap is generally monolithically cast with the staining. So, this well cap is transmit the load to the staining. Okay. No, what is staining? Staining is basically the main body of this well. Okay. So, that shaft we are talking about. So, this is the staining, which is the side concreting walls. This is the main body of the shaft. So, this staining and the top well cap are cast at a time, and this the purpose of this staining, it transfer the load to the subsoil. Then the crab is this one, this is the well crab. So, this is the crab. So, this helps to process the sinking. Cutting edge, it cuts into the soil during the sinking. Then bottom plug, so this is the bottom plug, it also helps to transfer the load to the substructure. Then top plugs, so this is the top plugs, and in between bottom plug and the top plug, this is the sand filling. So, top plug, it provides contact between the well cap and the sand filling and help the transfer the load through the sand filling. Okay. So, these different components, and then what are the different shapes of the well. So, circular shape is the most common shape of the well. In addition to that, there will be a rectangular shape of the well and other shapes are also described here. So, these are the different shapes of well. So, now we are talking about how we can determine the depth of a well, how we will decide that. So, to know that, we have to determine what would the scour depth for a particular site. So, that scour depth we can use by using the Lacy's formula. So, that is the D is the scour depth. Okay. So, Q is the discharge and F is the Lacy's factor, which is generally 1.76 root over m. M is the mean size of the particles, mean size of the particles in millimeter. Q is the discharge. So, now by using these equation, you will get the scour depth, and we have a chart by which also we can get that what is the this A value, which is the Lacy's factor, seal factor, we can get directly depending upon the particle size and depending upon the type of soil bed. So, that means medium sand, if the particle size is 0.3, mean that is the mean size of the particle is in millimeter. If it is 0.3, then the F is 0.96. If it is 0.5, this is F is 1.24. Similarly, boulders, if it is 90 millimeter, then it is 24.3. So, that F also directly I can use based on this particle size, or if you have a different particle size, you can using that F also by using these expression. You can calculate the F by using these expression. Then once I get the scour depth, so that means this code has given. So, there are two codes in the IRC and in the IS code. So, they have recommended to increase the scour depth or the maximum scour depth by this amount depending upon the different types of section. Suppose if it is a straight stretch, so that means the scour depth that you will get. So, maximum scour depth will be 1.27 times of that D. Okay. Then at a moderate bend, so this will be 1.5 times of D. At a severe bend, it will be 1.7 times of D. At a right angle bend, it will be 2 times of D. At upstream noses of guide bank, it will be 2.7 times of D. So, that means first we will determine the D value, scour depth, then we will determine the maximum scour depth. Okay. Now, we have to determine what will be the grebe length. So, grebe length, minimum grebe length is 1/3 of maximum scour depth. Okay. So, that is the recommendation. So, that means as per IS code 3955/190/67, the depth of foundation should be more than 1.33 times the deepest cover below the high flood level. So, that means suppose this is your high flood level HFL, high flood level, and then first you calculate the scour depth, then you will calculate the maximum scour depth. So, by this recommendation. So, this is the maximum scour depth. Okay. Now, the grip length will be at least, your depth of foundation will be at least here. So, suppose this maximum scour depth is say d dash. So, this one should be more than 1/3 of d dash. Okay. So, that means I should say that if this is the maximum scour depth, or that is also d dash from the high flood level. Okay. So, the total depth of foundation will be, so depth of foundation will be, should be greater than d dash plus 1/3 of d dash. Okay. So, that will be equal to this is d dash, this is I should say d dash 1 plus 0.33. Okay. So, this is 1.33 d dash. Okay. So, that is the IS recommendation, that your depth of foundation should be greater than 1.33 of the maximum scour depth below the HFL, high your high flood level. Okay. So, that means if the scour depth is d dash from the high flood level, then you have to provide at least 1/3 of d dash as the grip length, and then the depth of foundation will be at least 1.33 of d dash. Okay, that is the minimum requirement. So, generally it is more than that. So, and another this is the recommendation is given. So, based on that we have to design our well, and then remember that this 1/3 of d dash is the grip length. So, 1/3 is the minimum requirement of the grip length. So, in the next class I will discuss that what will be the thickness of the concrete seal in open caisson or well. So, because if you see the one particular cross section of a caisson. So, here what is the construction technique I have discussed, that first this once it is reached the bearing strata, then the concreting is done, okay, and under water. Even when the for pneumatic caisson also the working chamber is filled with the concrete. So, for the open caisson this concrete is done under water. So, that means what would be the thickness of this bottom plug, or what would be the thickness of this concreting, because when there is a concrete is done, then basically the shaft is there will be a buoyancy force this which is acting upward direction at the bottom of the shaft. So, you have to provide sufficient thickness of this concrete, so that that force can be taken care, otherwise it will go upward direction. So, how this where this buoyancy force can be taken care. So, those things will be discussed in the next class, because then based on that we have to decide what will be the required thickness of this concrete for the open caisson. So, that I will discuss in the next class, the thickness of the concrete seal which is applied during the open caisson, so that we can prevent that buoyancy force, and then we will provide, there are other issues also. So, those will be discussed in the next class. Thank you.